Hello everyone. So today we will start the topic with two-port network. Okay. So basically we will start with two-port network analysis. So far whatever circuit we have discussed, it was all two-terminal network. It was all two-terminal network. So what does this word port means? A port means two terminals, right? A port means two terminals. Now, for example, so if I just draw a simple voltage source, suppose if I draw a simple voltage source like this, so let's say this is one voltage source, right? So let's just connect the terminals. Okay, so let me just mark all those terminal. One is positive terminal, the other one is negative terminal. That is the conventional. This is the conventional notation for any mm, for any voltage source, right? And now let's say it's a 5-volt battery source or any DC voltage source. So for simplicity, I have considered here 5-volt voltage source. So it can be AC source as well. So now you can see, so this is the source of any network. This can be used as a source of any network, right? A voltage source. Now it is connected across two different terminals. So this is actually a two terminal. So if I connect the same with equivalent network, equivalent circuit, with another equivalent circuit, so it will be a one port network because it consists only two different terminals, one positive terminal, the other one is negative. Now this is one port. So if I just now connect the same with, let's say, one load resistance like this. So this is suppose the rest of the network, and this is any resistance having value, let's say 10 ohm, right? So this is example. This is an example of one port network. So this is an example of one port network, right? Now the voltage current relationship of the same can be represented with this, that V equals to I into V equals to uh, I. If I consider I amount of current is flowing through the network, this is IR. So I'm considering that I amount of current is flowing through the network like this. So suppose this is the network and this is I amount of current is flowing. So this is, let's say, I amount of current is flowing. So with this we can represent this one port network. So now this kind of networks we have seen, we have solved several examples by applying KCL, KVL. We have used different network theorems for analyzing those kind of networks. Now today we will start with two-port network. So let me first give you one example of two-port network. So two-port, now this is very clear to us. This piece of information is very clear to us that two port means four terminals. So basically we will have four such terminals, four such ends, right? So each pair of terminal will form one port. So this is a general, very general block diagram of a two port network, right? And this is the equivalent linear two port network, the equivalent impedance part of the same. So not impedance part of the same, we will be talking about all those parameters. Okay, we have different form of representation. We have impedance form of representation. We can calculate equivalent admittance from any network. So we have a lot of things to discuss. So now uh, so this is a general diagram of a two-port network where V1 is the input voltage of the of this input port, right? So here in this general representation, we will take up one port as input port, and we will take up the other port as output port. Okay, other port as output port. So this is, here is the source voltage, that is the input voltage of the network will be connected, which will be providing I1 amount of current to the rest of the network. So this is the form of representation, and this arrow indicates the direction of the input current quantity, which is I1, right? So V1 source, input voltage source, is providing I1 amount of current which is flowing towards the network. So this is the interpretation. Now we are done with defining the input port. Now I will come to the output port. So here I forgot to just write down output port, so we can write it as output port, right? So here in the output port also we have two terminals, right? We have one positive terminal, so we have one negative terminal. Now here this V2 is the output voltage, okay, at the end terminal, across the end terminal, or you can say output terminals. This is actually output port. So this is output port voltage, which is denoted with V2, right? Which is denoted with V2. And this is I2, which is the amount of current offered by the V2 voltage source. And why the notation is invert? Here is a trick, little trick. So I1 is this arrow is showing the direction of I2 current, which is flowing through the network, right? So this is the end terminal. We know some kind of load will be connected across this terminal, right? So from this output port, I2 amount of current will be flowing, because this is, as a whole, this is a closed network, no terminal is left open, so it will be flowing towards the network only, because this is the end terminal. So that's why the direction of current is I2 here. The direction of current is I2 here. So this is V1, which is providing I1 amount of current at the input port. This is V2, equivalent output port voltage, which is providing I2 amount of current to the rest of the network. And this total box is representing the rest of the network, which we have within the circuit. Now, let me just give you one example, very common example of transistor. Transistor is a three-terminal device, we know. So for single port network, while we will be analyzing any diode circuit, we have seen sometime if it is forward bias, that time with proper biasing the diode will, suppose we have a PN junction diode, it will conduct, and if we put it in a reverse bias mode, it will not conduct. So that is basically a one port circuit example having two terminals. And itself, if you consider the diode, if you take up any diode for any experimentation purpose, you can see it's a two terminal device, right? We have two terminals for the same. So now here in case of transistor, it's a three terminal device. So many a times while we have seen different applications of transistor, we have seen it can be transistor with proper biasing to the, all the emitter, base and collector terminal. Transistor can be operated for switching application, it can be operated for amplifier application, but we need to put certain kind of specific biasing to all the junctions. So these are, in case of transistor, common emitter mode, common base mode, common collector mode. These are very three popular mode of operation and configuration of transistor, while we connect the transistor in that particular mode, and accordingly we design our required circuit for our required application. So this common base, so that time that common base is basically we are putting that configuration as a two-port network representation, where both the input port and output port will have a common terminal. It can have a common terminal, but it's a two-port network representation. So that's an example of two-port network. Now we will see uh, what kind of analysis, how the voltage current relationship uh, we can establish from this sort of representation from two port network analysis. So here basically what we do, so we calculate certain two port parameters. uh, they are two port parameters. So we have some popular two port so we have some popular two port network parameters which is known as Z parameter model. We have Z parameter model, we have Y parameter model. Now what are them, what are the details of the same, I will discuss one by one. So today we will take up the Z parameter model, which is known as impedance parameter model. We also have so these are main four parameters which we consider in case of two port network. We used to calculate them. Okay, so we have Z parameter, we have Y parameter, we have H parameter representation. Also we have ABCD parameter representation. So Z parameter, now I will discuss, that is actually our impedance parameter, right? That is our impedance parameter. And this is Y parameter, means admittance parameter, which is reciprocal of impedance parameter. H parameter is hybrid parameter model, while we will take up both impedance and admittance later. As our discussion, we made some progress with our discussion, we will see the H parameter model and ABCD parameter model as well. So ABCD stands for this is basically transmission parameter model. So so let's not talk much detail about the other ones. So let's just get started with Z parameter model. So now we will start with Z parameter model. How we can represent the same, what kind of uh, voltage current relationship we can have, what does it mean, Z parameter model, we will just try to uh, observe that. Now let me tell you one thing. Whatever mathematical equation, I mean relationship, I will try to write down, I will try to formulate the input and output voltage and current parameters in terms of certain mathematical formulation. So everything, for all the equations I will refer only the basic circuit, the one I have shown you just now. Just before that I have shown you this one, so I will be referring this circuit only, right? Okay, so now so let me just start with uh, writing down some voltage current equation. So let's say V1. V1 is our input voltage. So first let me just write down the equation and then I will explain. So next is this. Did I put space? Let me just um, right. So this is one equation. I have written V1 equals to Z11 I1 plus Z12 I2. Now I will write down the next equation, which is V2. V2 equals to Z21 I1 plus Z22, right? Z22 I2. So here I have written two equations. Now how I have written these equations, I'll come to that point later. So if I just try to form some kind of matrix from the above two equations, can I put it like this? I guess I can. I can put it like this, right? So let me just draw the matrices. Uh, so now from the above two equation, if I represent them within a single um, matrix equation, if I just try to formulate the same, so I think I can write it down like this. So this is, let's say, V1. We have one more term. So this is V2. Now you see in the in case of this coefficient value, so four terms, voltage and current term, V1, I1, V2, I2, these are known to us, right? And we have marked them in our previous diagram. So let me just, so this 1 1 1 2 2 1 2 2, these are basically denoting matrix position, and this is a 2 cross 2 order matrix. So let me just write down all the parameters. Let me just write down. Let me just write it down here. This is Z11. Fine. This is Z12. This is 1 1. This is 1 2 position. This is 2 1 position. Now we will put it in the 2 1 position, and we have one more position left, that is Z2. And now I will um, just put down the other terms here. This is I1. So this is, the other one is I2. So now if I just write it down, now if I just expand this matrix, so you see what you will get. V1 is Z11 into I1 plus Z12 into I2. You will get exactly. So if I just mark them, with equation number, one is 1 and let's say the other one is 2. So if I just expand these two matrices, I will get uh, the above two equation. This is V1, other one is V2, and we will get the same from this matrix. So matrix, this matrix is known as Z parameter matrix. So what we did basically, so this is our linear two-port network we have. This is a very general network, and whose input port and output port voltage and current parameters are known to us, and we have formulated uh, the impedance parameter model from the same. Okay, so if I write down this, that means the impedance parameter model can be represented with this Z matrix. Okay, so this is known as Z matrix. Okay, so whenever I will talk about impedance, the unit will be ohm. The unit will be ohm, right? Now the question comes, how I will calculate this. uh, so basically V1, V2, I1, I2, this parameter will be known to us, and we have to get the equivalent impedance parameter matrix, which will obey this equation 1 and 2 for the given or provided two-port network uh, circuits, right? So now the question comes, how we will calculate Z1, Z12, Z21 and Z22. This is simple. Here we have only two equations, but we have four variables to calculate. So this is very obvious. We cannot do that, right? So at a time, what I will do, once I will make I1 equals to 0, the other time I will make I2 equals to 0. So let me just, whatever I am telling you, let me just proceed with the same. We need to solve, let me just write down, to solve um, equation 1 and 2, let I1 equals to 0. Let's I1 equals to 0. So if I say I1 equals to 0, what will happen? This two term will be 0. So the moment I say I1 equals to 0, that means what? That means what? Your input uh, terminal current, input port current will be 0. When it will be 0? If you open the terminal. If you keep it open, if you just open this terminal, the you across the open terminal you will get the equivalent voltage, but you cannot get any current because it's open path, so no amount of current is flowing through this path, so you will get that. So basically, to make I1 equals to 0, the moment I will say I1 equals to 0, that means what? Open input port. Open input port, right? So now easily you can just write down, you can just obtain the value of so now the equation becomes v1 equals to z12 into v2, sorry, I2. This is I2, and the other equation you will get, if I just put a enter, you will get v2 equals to z22 I2. Fine. So easily from here you can get the expression of Z11, and what I can say, you will obtain these two parameters. You will obtain these two parameters Z11, the value of Z11, and uh, so this Z11 and Z22 value you can obtain by making I1 equals to 0. So in the similar way, how you can get the other one? Let the other case is, let I2 equals to 0. We will put I2 equals to 0. So if you put I2 equals to 0, that means what? That means what? Again, you will open output port this time. This is case 2. You will make the output port open. And here what equation you will get here? So here the equation becomes V1 equals to Z11 I1. Here we don't have any I2 term. We have made it 0. And we will get V2 equals to Z21 I2. Sorry, I should have written it as I1. So yeah, this is the equation. So now from here you will get the rest of the two parameters like this, Z11 and Z21 you can get. So this is our Z parameter model. How you will basically you will do that. So let me just show you once how you are going to do that basically. How you are going to do that. So let me just take this picture, the same figure. So if I just put it here, if I just put it here, so let me just take the same pen. I denotate for making I1 equals to 0. So it will be open. This in this case, I1 equals to 0. Okay, I1 equals to 0. This is case 1. And in the similar way you will this is case 1. In the other case, in the similar way you will make I2 equals to 0 and you will calculate that. So basically you have two equations. You are supposed to calculate four parameters because the Z matrix contains four elements. It's a 2 cross 2 order matrix, and at a time you will consider I1 or you will consider I2. Yeah. So this is our two port general two port network general block diagram, and that's how we can calculate the equivalent impedance parameter model, that means Z parameter model. So that's all for today. In our next class, we will start with Y parameter model. Thank you, everyone.